Hello, physics students. It's Mr. Gopal here. And today I'm here with an important fundamental lesson that has to do with free body diagrams and forces. In particular, this lesson is about gravitational force and how it changes, or how the way that we diagram and figure out forces changes when we have objects on inclines. So a little bit of background. We've already studied objects at rest on a surface. We know what a free body diagram entails there. And I'm going to draw one of those in a moment. Now we're going to draw one in an incline after. We're going to compare those. We're going to figure out how to move forward in terms of how we understand all of the forces and their components. And so we want to be able to describe an object's center of gravity at the end of this lesson. We want to be able to resolve the weight vector of an object placed on an inclined plane into the normal force, which happens to be equal to the force of the object that is perpendicular to the plane, and then a parallel force, which pushes the objects down an inclined plane. So there's a lot of vocabulary there, and I'm just going to go back quickly to the focus question, which is what information can we get from the weight vector of an object on an inclined plane? And this stuff is hard to talk about in the abstract. So in this lesson, what I'm going to do is I'm going to work through a diagram in real time and help you understand all the forces. So in order to do that, I'm going to pull up my whiteboard. And just to review, the first thing that I want to go over is what happens when we have an object just at rest on a surface. Okay, so let's say here's a table, and then on top of that table, I have a box, and it's resting there. As you've already learned, we know that all objects on Earth experience the force of gravity, which I'm going to represent with the green vector. We know that gravity, the force of gravity, is pulling an object towards the center of the Earth. And so the way that we diagram that in a free body diagram is to put an arrow from the center of the object, or the center of mass of the object, you could say, pointed directly downward. Okay. Now we also know that the box, or whatever the object is, it's not going to go through the surface. So if we were to say the object is my phone and it's resting on my table here, I don't see the phone go through the table and fall through the floor as well. So we know that there must be some sort of force counteracting it, because that phone right now is at rest on the table. And we call that force the normal force, which I'm going to diagram with an upward orange arrow. These forces, because the net force on this object, if it is at rest, is 0. These forces are equal in magnitude and opposite direction. And I'm just going to label them according to the names that I just gave. So this would be Fn. That's the normal force. This I call Fg. You'll also see this referred to as just W for weight, which we know to be a force, the mass times acceleration due to gravity. So the mass of the object times acceleration due to gravity. Let me just label those really quickly, and we'll have that reference up here. So the normal force is the force, the upward force of a surface on an object resting on that surface. And this is the force of gravity, or weight, and that is equal to the mass of the object times acceleration due to gravity. We know if we're on Earth that that is equal to 9.8 meters per second squared. Now we come to the situation with an incline. All right, so I'm going to draw an incline over here. And so it's like an inclined plane. You can think of it as a slide or just an angled table, however you want to think about it. And so much of physics is, well, how do I take what I already know and now make the situation slightly more complicated, so that I can figure out in more detailed ways what happens in a way that approaches the complexity of life. And so you do this several times, and if you were to study physics in undergrad, you get to even more complicated scenarios. We'd add in air resistance, we'd add in other factors as well. So let's say I know that that line is not directly on the surface of the inclined plane. but let's say that it was, and I got my box here now. So here's my box, and let's start diagramming and see where we end up. So the first thing that I always like to diagram when we're dealing with objects on Earth is the force of gravity. So I'm going to do that with a green vector again. And just like before, crucially, it's going to go from the center of mass and it's going to point straight downward, okay? And I'm going to label that FG. Actually, I'm going to make it a little bit longer. We'll see why, just so I can label it outside of this incline. All right, so that's my FG. Let me label that really quickly. F sub G, or W for weight. Okay, now we know from studying vectors at an angle, whether they are acceleration or velocity or force vectors or another vector quantity, that we can break them down into X and Y components. Okay, and when we're dealing with an object on an incline, we break those down according to the angle of incline. And so instead of dealing in terms of X and Y like we would with a projectile fired at an angle, we're going to deal with forces that are parallel or perpendicular to the angle of incline. And so the first thing you want to think to yourself when you're diagramming this is, wait a second, the normal force is pushing perpendicularly up from a surface. So we see that quite simply in the scenario up here, all right, where I have this scenario that I just circled. Since the plane is flat, there's no incline on it, we can just draw an arrow straight up. But the point is that whenever we talk about a normal force, we're talking about a force that's perpendicular to whatever surface we're dealing with. So I'm going to draw the normal force on my diagram. Let me draw it in purple. And so that is roughly perpendicular or at a 90-degree angle to the surface that we're dealing with. And I'm gonna label that F sub n. And actually, once again, I'm gonna make it a little bit longer, and you're gonna see why eventually. So that is F sub n, just like before, okay? And now we know that one of the components of the force of gravity, because we're dealing with this at an angle, we need to break it up into its two components. One of those components is perpendicular to the angle of incline. And that perpendicular one is going to be equal in magnitude and exactly opposite in direction, or 180 degrees opposite in direction to the normal force. So I'm going to draw that one in blue. And there you go. And I'm going to label that according to some conventions you may or may not have seen in class. And that's going to be F sub G perpendicular. And this is the way that I express perpendicular. All right. Now the final component. So I have my perpendicular component. I need my parallel component. That is going to be parallel to the angle of incline and from the center of mass of the object. And so that's going to look like this. I'm going to make it in magenta. And that one points, as you can see, directly parallel to our red angle of incline. All right. Now I'll just label a few other things and explain what is happening here. So first of all, we have our angle of incline, which I'm going to label as theta. All right. Let's say that it equals 30 degrees. Usually we're going to deal with simple angle measures, not really kind of weird or decimal values. We're going to deal with cleaner values in these scenarios just to help you focus a little bit less on the trig and a little bit more on setting this thing up. But one other thing that I can recognize is that I have 2/3 of a triangle here when I look at my blue and my green vectors, all right? You can see my green force of gravity vectors pointing straight down, and then I have my blue perpendicular force of gravity component pointing there. And if I were to grab this and move it down, we could see that we have an exact triangle, all right? I'm gonna move it back there and I'm gonna draw another one. And I'll draw that one down here and then label this diagram to remind you that this vector that I just drew is exactly equal in magnitude and direction to the one above. So they are both FG parallel, all right? Draw that in black. So right here, FG parallel, we represent parallel with two vertical lines next to each other. This one is also, undo that. This one is also FG parallel as well. And so the thing that can be a little bit confusing about these diagrams is to recognize that my multicolored triangle, my green, pink, blue one right now, that is a similar triangle to the entirely red triangle, the large triangle that represents this inclined plane. Okay, just to remind you from geometry, a similar triangle is one in which all of the angle measures are equal, but the sides may not be the same exact length. So I can make the same type of triangle in terms of angle measures, but it can be smaller and larger than the other one that it is similar to. Okay, so obviously the vector sizes you can see are not the same size as the components of the inclined plane. They're smaller, but the angle is the same. And if we were to rearrange this triangle appropriately, I would have my green vector corresponding to the hypotenuse. I would have my blue vector corresponding to the base. And then I'd have my pink or magenta vector corresponding to the height of the triangle. And when I suss all of that out, I realized that this angle here happens to be theta as well. Now you might ask yourself, why is that important? Well, it's important because we can actually start to get a little bit more detailed about what the force of gravity perpendicular and what the perpendicular component of the force of gravity and the parallel component of the force of gravity are actually equal to. And I can use trig in order to figure that out. So as I can see, I have the side opposite my theta as my pink vector, all right? I'm just gonna draw an arrow temporarily just to illustrate that, and then I'm gonna delete it. So I can see that that angle theta is facing my pink side, therefore it's the opposite leg relative to theta. So undo that. And I happen to know that the sine of an angle, in this case theta, that is equal to the opposite over the hypotenuse. Now, if I fill in one thing, I know that the hypotenuse itself, that's equal to the force of gravity, the overall force of gravity, all right, the original vector. How do I know that? Well, we know that that green vector that I drew at the beginning, that's the one going straight down. That happens to be the hypotenuse. So that is my force of gravity. So in this case, the sine of theta is actually equal to the opposite leg divided by the force of gravity. Therefore, if I work this out, and I'm going to do it up here because I'm running out of room, I can say that the opposite leg, if I multiply both sides by f sub g, is equal to sine of theta times the force of gravity. We usually write it the other way around, so I'm going to rewrite it right below. Fg sine of theta is equal to the opposite leg. And so therefore, I know that the parallel force of gravity, Fg parallel, is equal to that, all right? And I'm just going to write that relationship down here. Fg sine of theta. Now, likewise, I'm not going to go through all of the calculations because I do want to get on to a problem, but I can say that the perpendicular force, because if I circle it right here, I can see that it's the adjacent leg, or the leg adjacent to theta. All right, let me undo that. It's a little bit messy. I know that's the adjacent leg, and by the same series of calculations, I can conclude that that is equal to f sub g times the cosine of that angle, which we represent with theta. So now I have these working equations or formulas, you could say, for calculating the perpendicular component of the force of gravity for an object on an incline and the parallel component. The parallel component is calculated as the sine FG times the sine of theta. The perpendicular component is calculated as F sub G times the cosine of theta. One final thing that I'll mention is that what happens in these problems is that we know that our normal force and our perpendicular force of gravity are equal and opposite, as I mentioned way earlier in the video. So that means that these two vectors, all right, I'm going to circle each one of them, black, this one, and that one, they will cancel each other out. And so usually, if I know this object is accelerating down, then I know that that is due to the parallel force of gravity. In other words, the perpendicular force of gravity is not going to be involved in the ultimate behavior of the object on an incline. Now that we've established all of that, what you want to do is maybe take a screenshot of all this and start committing it to memory. All right, so just a few things that we went over. The normal force and the perpendicular force of gravity are equal and opposite. We can calculate the normal force by setting it equal to Fg cosine theta. And if we happen to know the mass of the object and the angle of incline, then we can plug in there, because this would be equal to mass times acceleration due to gravity times the cosine of theta. All right, so I can make both of those calculations that way. Obviously, also, just as before, I could calculate the overall force of gravity, which is pointing straight down. That's the green vector. And then finally, I can do the same sort of calculation of mg sine theta. And I can calculate the parallel force of gravity, or the parallel component of the force of gravity. Fantastic. So we've got all of that. I'm going to stop sharing. And now let's go back to the slides. Now that we know all of that, let's see if we can apply some of this stuff to a problem. So we've got a car weighing 12,000 newtons parked on a 36-degree slope. Find the force tending to cause the car to roll down the hill. As I said before, and I'm going to do it quick and dirty and all in black so you can really see it in this blue space next to the slide. So I've got my angle of incline of the street right here. Okay. And then I've got my object. I'll do that one in red so it pops. Here's my car at an incline parked. We want to know what's the force tending to for the car to roll down the hill. Just to review again, here's my force of gravity pointing straight down, and I can break it into my two components, Fg sine of theta and Fg cosine of theta, and I'll just label those as the parallel and perpendicular forces. So that equals Fg cosine theta. And up here, my parallel force, that is equal to Fg sine of theta. Brilliant. Okay, and so as I said before, the perpendicular force, that will be canceled out by the normal force, which I'm going to draw right here. It's equal and opposite, F sub n. And so those two are going to cancel out. So if I'm thinking about what is the force tending to cause the car to roll down the hill, I have to think about Fg sine of theta. Now, crucial thing, they tell us that the car weighs 12,000 newtons. That means that F sub G, in other words, W, is equal to 12,000. I don't need to take its mass and multiply by acceleration due to gravity. In this problem, they've already done that for me. And now we have the value of theta. So I'm just going to write these two things here. We know that F sub G is equal to 12,000 newtons. We also know that theta is equal to 36 degrees. And just as I said, to reiterate one more time, Fg perpendicular cancels out F sub n, or the normal force, And so if we're dealing with components that might cause the car to roll down the hill, that would be the parallel force of gravity or the parallel component of the force of gravity. So all that remains is for us to set up that equation and plug in the numbers. So we know that the parallel force of gravity is equal to Fg sine theta. And now I'm just going to plug in the correct values. So I'm going to plug in 12,000 newtons for my F sub g. And then I'm going to plug in the sine of 36 degrees. Now, remembering that the sine of 30 is 1/2 tells me that perhaps the sine of 36 will be a little bit larger. So grab your calculators, I am too, and let's calculate this thing. So it was just a little bit more than 1/2. And so if I plug in and I calculate, I get 7,053.423, etc. And now if I'm observing significant figures, I know that I have 2 significant figures here and 2 here. Therefore, my answer should have 2. And if I round up based on the 5 here, I should get a final answer of 7,100 newtons. I'm going to write that properly, sorry. This would be a 1. Final answer. All right, so I hope this is a very helpful introduction to the forces acting and the components of forces acting on an object on an incline. Things to look out for before I let you go. We will have scenarios where objects are moving at a constant velocity or accelerating down the plane. The one thing that we didn't cover in this video is the idea that sometimes there will be a force of friction. And of course, friction is a drag force, which means that it is going to oppose the direction of motion. So for example, if a car is rolling down this hill in the picture, there would be friction from the gravel and asphalt on the road pushing against it. And so if that pushing against it leaves it moving at a constant velocity, we can conclude that the force of friction is equal to the parallel component of the force of gravity. However, if the car is accelerating downward or it is decelerating to a stop, then we know that the force of friction is either greater or less than the parallel component of the force of gravity. These are nuances that we'll go over in problem language as we encounter more problems. For now, I hope this is a helpful introduction to a very important topic, and I will see you soon.